Hi everyone, my name is Thomas Kim. Today is November 6, 2019. This is my 16th episode about linear algebra and threading building blocks. In this episode, we will learn how to use parallel reduce, block range, grain size, and random number generator stopwatch. Using these elements, we will implement parallel algorithm for Laplace expansion. If you haven't watched my previous video, Problem Solving Strategy, Laplace Expansion in C++, please double-click this link because my current episode continues from my previous session. If you haven't watched this video, please watch it now. Click Show More. Double-click this link to download the complete source code from our previous episode. Show in folder. Unzip the folder. Rename the folder name 16 Laplace Expansion Parallel. Copy the folder path. Copy. Paste it to your working folder. Now start Visual Studio Code. If you open the folder, you can find 16 Laplace Expansion Parallel. From 16 Laplace Expansion Parallel folder, double-click matrix. In our last episode, we created this function and the matrix element type is double. In episode 13, we implemented determinant Leibniz serial, and episode 14, we implemented determinant Leibniz parallel. Now start command prompt dir cd 16 Laplace expansion parallel. We are using Clang compiler std C++17 matrix.cpp ltbb malloc, hit enter. CLS, all result is 18, seems to be working. Now change it to int. Now element type of matrix is int. Now let's build once again. Hit enter. Now the value is different. Parallel Leibniz determinant gives wrong answer. In this file, determinant Leibniz parallel, I made a mistake here. We declared atomic, det is not initialized. So I fixed like this. Then we build again. Now it is fixed. So I made a mistake. Episode 14, when we implement Leibniz determinant parallel, we made a mistake. Now scroll down, find determinant Laplace serial, copy, paste, and rename it determinant Laplace parallel atomic. Then scroll down. We will turn this part into parallel. Before we turn this part into parallel, I will modify this part a little bit like this. Auto cofactor, copy this part, copy, paste. We will make like this. Then we can modify this part, cofactor. Also, we can fix like this, like this. Please note that the function name is determinant Laplace parallel atomic. In matrix.cpp, I say atomic, parallel Laplace determinant Laplace parallel atomic. It is still serial, but we will turn it to parallel very shortly. In the command prompt, build once again 300. We missed semicolon here. Build once again A. All works the same. Now here we will turn this loop into a parallel loop like this. Now here auto handle parallel, we will just capture all auto J like this, then TBB parallel for size T, this is 0, this M columns, then handle parallel. Now in this part, STD atomic element type DET, we declare DET, so we don't need this. We delete. Now in this body, I copy paste it. So we don't need this. So this D is shared among multiple threads. Here, now we return DET. But this part does not work. Instead, we can do like this. Element type, old DET, DET, new DET. I translate this part is true, then old DET minus cofactor, else old DET plus cofactor. So I translated this part. Ctrl K, Ctrl C. I will change it to element type like this. Okay. Now while DET compare exchange strong old DET new DET. If it fails, then we have to do this again in the loop. Please note that we are using atomic. So I translated this part like this. So I will copy this, cut, paste it here for your reference. Also here. Now we call this function here. Now let's test if it works. 318, 318. Sorry, I missed semicolon here. This is lambda closure, so we need a semicolon here. Build again. It works as expected. This parallel for use indices 0, start indices, and end indices. We will introduce blocked range. Before I introduce blocked range, I will make a member function. I will remove some space like this. Now scroll up. In class matrix, There is 3-member data field, 2 instances of size t, m rows, n columns, and this is array. If you want to create a thread-safe container class, you never release or leak data member field. But I will leak data member field in public section like this. Its array type is container type, so reference array return this m array. This is awfully bad practice. You should never leak data member field to public interface directly or indirectly. But for convenience, I will do it for testing purpose. Now in matrix, I will make a namespace alias. CHR means chrono random. Talk play fun, chrono random. I introduced a new namespace alias. Then here I will make the size, for example 5, using element t, double element t. This is n by n matrix. I introduce random number generator, auto generator, CHR, chrono random, this namespace, colon, random generator. We generate random numbers of type element, start range and end range, random numbers from -10 +10. We are creating random number generators that generates instances of type element t ranging from -10 to 10 inclusive. Now I will delete this part. Chrono random field, our matrix M, array generator. Now we will build this function. We are generating 5 by 5 matrix element using random number generator. I said exposing private data member field through public interface is really bad practice. In real code, you should never do this. But this is for demonstration purpose only. Now we will build CLS. So we generated random numbers. The result is the same. For convenience, I will change it to int. Okay, let's try it. Now with the integers, the result is all the same. It means they are correct. Now in this file again, this Laplace parallel atomic. Now we will convert this range to blocked range like this. I will copy TBB blocked range size t like this. Now we have to modify this part too. This callback's parameter should also be changed like this. TBB blocked range size t reference range. it should be constant, like this. Then in here, for order I, J, range begin, J is not equal to range end, plus J, I open a block, I close block. Now I will indent it like this. Okay? So this is block range of size T. Using this range, we made another for loop. Now scroll down. So this type should be identical. Instead of doing this, this is identical. So I will copy once again, paste. I will disable it. In C++17, this is also possible. Okay? This is possible only in C++17 standard. And scroll up. I will copy this, paste. I will disable it. Then we can say auto range. Okay? Auto range maps to constant range. For your understanding, auto range can map to integer reference as well as constant integer reference. Now we will run once again. CLS. So this function, atomic parallel Laplace determinant, works successfully. Now here I will modify it into 7 or 8. I will introduce another thing called, I will copy once again, grain size. Okay, we use grain size 2. Then here I will introduce mutex using mutex T, TBB, spin, mutex. I introduced a type, mutex T, mutex. Because we captured all as reference in this block, I made a new scope, mutex T. We defined this type here, scoped lock. We use this mutex as argument, std cout grain size, like this, range end minus range begin. Please note that range we received as parameter. This is to display range, grain size. Okay? Now we build once again. So grain size is 2. I hope you understand what grain size means. Okay, let's see if we delete this part, grain size, field again, default grain size is 1. If we add grain size 4, so grain size is 2. So this grain size is used to range inside the loop range. Now I will turn it to default. Now you understand the grain size, blocked range. I will turn this algorithm using parallel reduce. So far, we used atomic for parallelize our algorithm, but there is one drawback. This atomic DET is shared among the threads. By sharing, we introduced atomic operation here. Using atomic operation, serialize our algorithm. This atomic operation should be very short period of time. If the operation takes long, then you should not use atomic. In this case, this operation is very short, so we can use atomic. But if we turn it into parallel reduce using thread local, then we can further optimize our algorithm. Now I will copy this function up to this point, copy, and paste it here, scroll up. Now I change parallel reduce. I modified the function name, scroll down. I will remove some redundant code. We do not need mutex because we understand what is grain size. Okay, so I will remove this block. Also, we will remove this part. We removed this part and restore it. Ctrl K, Ctrl U, I restored. Also, I will restore it to DET like this. And I will delete this part too. This is basic parallel for loop. Now we will convert it to parallel reduce. Now this is the first step. I will also delete this and remove this comment too. Now auto DET, or it can be element type DET. Okay, so I just say auto. Now we received DET through parameter. We don't need this. Okay, and we modify it into parallel reduce. Up to this point, we need to provide initial value, default value for DET. So element type, this is 0 default value. This handle is the same. This is a block of range because we use the range. Now we have to sum up. We have to sum up each block of data. To sum up, auto sum up. I will make another closer. Auto left DET, auto right DET we take two instances of det, return left det, right det. We sum up all local thread instance. This det internally will be created like this. Thread local det or something the like. I will explain about thread local in some future session. And we have to provide, don't forget semicolon here, sum up. Then it returns this det, summated det, return, like this. So this is determinant Laplace using parallel reduce. Please note that in this code, this det is parameter. We have not used lock synchronization mechanism nor atomic. We use thread local, so it is most efficient way. Now here I will copy this function, then it is parallel reduce, Laplace determinant parallel reduce. Now in the command prompt again, we have to return from here, return det. We have to return det. Okay? Also, I will modify it, this part, simplify this part, like this. Det equal j modulo 2 is 1. Then det, this det comes from here, cofactor, else det plus cofactor. I simplified like this. Don't forget returning this parallel handle closer. Okay? Now we build once again. CLS. Now parallel reduce also works. I will disable this part. For the time being, when you try this code, please enable this part of code to try by yourself. Let's build once again. CLS. Now everything works fine, correctly. Even if you don't understand parallel reduce algorithm, don't worry. I will explain about parallel reduce in gory detail in future episode. For the time being, please bear with me. To understand parallel reduce, I have to cover thread local storage first. So, in future episode, I will cover thread local storage, how to use them, how to implement parallel reduce, etc. Up to this point, we implemented determinants using serial Leibniz, parallel Leibniz, serial Laplace determinant, atomic parallel Laplace determinant, parallel reduce Laplace determinant. This algorithm is very inefficient. Both Leibniz formula, Laplace expansion are very inefficient methods. The reason I introduced these determinants, even though these are very inefficient, is to help you understand what is parallel algorithm, what is serial algorithm, also how to implement these fundamental ideas. Numerically, this algorithm is inefficient, but algebraically or analytically, this method enables us to have better understanding about determinant. In future episode, we will implement determinant using Elliott decomposition or some other numerical method. Up to this point, we used Clang compiler. if you want to use GNU compiler, compile like this. GNU compiler also should work. If you want to optimize alphabet O3 switch, then it is optimization build. Optimization build also works. Now, if you want to build using Microsoft compiler, CD16, Laplace Expansion, parallel, I will make it bigger, CL, EHSC, STD, C++17, O, alphabet O2, this is optimization switch, matrix.cpp, TBB, MALLOC, LIB, FE, m.exe, hit enter. CLS, and Microsoft compiler also works perfectly. By the time you watch this video, I will post this script in the description section below this video. You can double click this link and download the complete source code. In future episode, I will talk about Cramer's rule. Please subscribe to my YouTube channel. Thank you for watching.